All right, let's go. Number 7, eternal inflation and the false vacuum. The most conservative answer physicists can give is also the least intuitive. Before the Big Bang, there may have been something like space and time already expanding, just not in the form we recognize as our universe. Eternal inflation begins with a real mechanism rooted in quantum field theory. Inflation itself is not speculative. It was introduced to explain why the universe is so large, so smooth, and so geometrically flat. The idea is that very early on, a field with extremely high energy density dominated spacetime, causing space to expand exponentially, not linearly, exponentially. In a tiny fraction of a second, distances grew by factors so large they erase almost all prior structure. But inflation has a dangerous implication. In many models, inflation does not end everywhere at once. Imagine a high-energy vacuum state, what physicists call a false vacuum. It is not the lowest possible energy configuration, but it can persist for a very long time. Quantum fluctuations allow small regions of this false vacuum to decay into a lower energy state. When that happens, inflation locally ends. Energy converts into particles, radiation floods space. A hot, dense universe is born. That event looks exactly like a Big Bang. On the largest scales, however, inflation keeps going. Space continues to expand faster than these decaying regions can consume it. The result is a cosmic background that never stops inflating, constantly spawning isolated bubble universes like ours. Scale this idea down. Inside a single inflating region, quantum fluctuations are stretched to astronomical sizes. Those fluctuations later become galaxies. Inside galaxies, gravity pulls gas into stars. Inside stars, nuclear fusion irreversibly converts hydrogen into heavier elements over billions of years. Planets form from leftover disks. On at least one planet, chemistry organizes itself into biology. Every irreversible step, fusion, stellar death, radioactive decay, traces back to the same condition, a universe that began hot, dense, and expanding. Eternal inflation claims that this beginning is local, not absolute. The tension appears when we ask what the false vacuum itself is doing in time. If inflation is eternal into the future, is it also eternal into the past? Some theorems suggest it cannot be. Even an eternally inflating spacetime seems to require a boundary, a point where classical descriptions break down. Others argue that quantum gravity may remove the need for a beginning entirely. The unsettling edge is this. Our Big Bang may not be a unique origin, but a phase transition, like ice forming in a supercooled ocean that never freezes completely. If that is true, then before the Big Bang was not empty and not chaotic, but governed by stable physical laws that still exist beyond our cosmic horizon. We are not at the start of everything. We are inside one outcome among countless others, drifting in a spacetime that does not notice us, but makes us possible.
Number 6, the Big Bounce and quantum gravity. If eternal inflation suggests that the Big Bang was not the beginning, the Big Bounce goes further. It argues that the Big Bang was not even a creation event at all, but a rebound. The conceptual anchor here is gravity itself. In Einstein's general relativity, gravity is always attractive. Compress matter enough, and space-time curves inward without limit. Run the equations backward, and the universe collapses into a singularity. Infinite density, infinite temperature, infinite curvature. Physics stops there. But singularities are not physical objects. They are warning signs that a theory has been pushed beyond its domain. Quantum gravity attempts to fix that breakdown. One approach, known as loop quantum cosmology, treats spacetime not as a smooth fabric, but as a structure made of discrete, quantized units. Below a certain scale, roughly the Planck length, space cannot be compressed any further. Geometry itself resists collapse. In this framework, a contracting universe does not end in a singularity. As density rises towards an extreme but finite maximum, gravity changes character. It becomes effectively repulsive. Collapse halts, then it reverses. A bounce. Cosmically, this means our expanding universe may be the aftermath of a prior contracting phase. Galaxies, stars, planets, and atoms all exist on the expanding side of a much older cosmic cycle. Track the causal chain downward. As the previous universe contracted over trillions of years, galaxies merged. Supermassive black holes consumed surrounding matter. Stars burned out, converting nuclear fuel into heavier elements, releasing entropy irreversibly into spacetime. Eventually, structure dissolved into a nearly uniform, high-density state. At atomic scales, electrons were forced into nuclei. At subatomic scales, protons and neutrons dissolved into quark-gluon plasma. Space-time curvature intensified until quantum effects dominated geometry itself. Then, the bounce occurred. The timescale is extreme. The bounce phase itself may have lasted only a fraction of a second, but it was preceded by an entire cosmic lifetime, possibly longer than the age of our current universe. Information before the bounce is mostly erased, but not necessarily all of it. Some models predict faint imprints in the cosmic microwave background, subtle anomalies in large-scale structure that hint at a pre-Big Bang geometry. The unresolved tension is entropy. Each cycle increases disorder. How can the universe bounce repeatedly without accumulating an impossible thermodynamic burden? Some proposals suggest entropy is diluted during contraction. Others argue that cycles are not identical and that only one bounce ever occurred. What destabilizes us here is not infinity, but continuity. If the big bounce is correct, then existence did not begin, it transformed. Our universe is not young in an absolute sense. It is the latest phase of a process that already knew stars, gravity, and time long before we did. The Big Bang becomes less of a birth and more of a memory boundary we cannot yet cross.
Number 5, a previous collapsing universe. Strip away the mathematics for a moment, and the idea becomes almost disturbingly simple. Before our universe expanded, another one may have been dying. This theory begins with the most basic equation in cosmology, the Friedmann equations, which describe how the size of the universe evolves under gravity. These equations do not prefer expansion over contraction, they allow both. What we call the expanding universe is just one solution. If gravity dominates and no unknown force intervenes, expansion slows, galaxies drift apart more slowly, eventually expansion halts, then it reverses. A collapsing universe looks nothing like creation. On cosmic scales, galaxy clusters begin to fall back together. Intergalactic space heats as gravitational potential energy converts irreversibly into radiation. The night sky grows brighter, not darker, as background photons blue shift. Over tens of billions of years, structure compresses. Stars collide more frequently, gas clouds ignite prematurely, black holes merge, radiating gravitational waves that cannot be undone. Entropy increases relentlessly. On smaller scales, planetary systems destabilize, orbits decay. Atoms are forced into higher energy states as ambient radiation intensifies. Eventually, matter itself loses its familiar structure. As contraction continues, temperature rises everywhere, not locally, but universally. The universe becomes more uniform, more energetic, and less complex. Time still flows forward, entropy still increases, but the arrow of cosmic evolution points inward. At the final stages, galaxies dissolve into plasma, atomic nuclei break apart, quarks roam freely in a dense, seething field. Space-time curvature grows so extreme that classical descriptions fail. In standard general relativity, this ends in a singularity, but if quantum effects intervene, as many physicists suspect, collapse may trigger a phase transition instead of an endpoint. The enormous energy density reorganizes spacetime itself, resetting expansion. The Big Bang in this picture is not a beginning. It is the last moment of a previous universe viewed from the wrong direction in time. The tension lies in memory. Almost everything from the prior universe would be destroyed by compression and thermalization, yet some global features like spatial flatness or low initial anisotropy might survive collapse statistically, not as information, but as constraints. This makes our universe feel less accidental. Its initial conditions may not be miraculous, they may be inherited. The destabilizing realization is quiet but profound. Existence may not require a first moment, it may only require continuity. Our universe could be the echo of a cosmos that already lived out its entire story, long before the first atom of our own ever formed.
Number 4. Conformal cyclic cosmology. There is another way to imagine a universe without a true beginning, one that does not rely on violent collapse or quantum rebounds, but on an almost unsettling kind of smoothness. Conformal cyclic cosmology starts from a subtle observation about time and scale. In physics, the laws governing massless particles, like photons, do not care about size. Distances can stretch or shrink, and the equations remain unchanged. This symmetry is called conformal invariance. Now consider the far future of our universe. If expansion continues indefinitely, galaxies will drift beyond one another's horizons. Stars will burn out over trillions of years. Black holes will eventually evaporate via Hawking radiation, a slow but irreversible process that converts mass into low-energy photons over timescales as long as 10 to the 100 years. At the end of that imaginable future, the universe contains almost nothing but radiation. No massive particles, no stable clocks, no meaningful way to define time or distance. In that state, the universe becomes conformally equivalent to a hot, dense beginning. In other words, the infinitely expanded cold future of one universe can be mathematically mapped onto the Big Bang of another. The end becomes the beginning, not through collapse but through loss of scale. Cosmically, this implies that our Big Bang was not the start of everything, but the continuation of a previous cosmic aeon. That aeon lived, formed galaxies, stars, planets, and black holes, and then faded into radiation. Once mass disappeared, the universe no longer distinguished between large and small. The next aeon began. Follow the chain downward. In the previous aeon, stars fused elements irreversibly. Black holes consumed matter, increasing entropy. Their evaporation erased the last massive structures. What survived was not information, but geometry. Some models suggest faint signals could pass between aeons, subtle imprints left by supermassive black hole mergers in the previous universe, encoded as anomalous patterns in our cosmic microwave background. The tension is severe. Does this violate thermodynamics? How does entropy reset? Advocates argue that when mass disappears, entropy loses operational meaning. Without mass, there are no clocks, no rulers, no irreversible processes to define time's arrow. The unsettling implication is that our universe may be neither young nor old in any absolute sense. It is one chapter in a book without a first page. Not cyclic in a mechanical way, but cyclic in a geometric one. The Big Bang becomes a boundary between meanings of time itself, not an explosion, a handoff.
Number 3, the quantum fluctuation from nothing. At this point, the theories stop relying on pre-existing universes and begin attacking the concept of existence itself. The phrase nothing in physics does not mean absence. It means the lowest energy state allowed by quantum laws. And quantum mechanics does not permit stillness. Even in a perfect vacuum, fields fluctuate. Energy appears and disappears. Virtual particles borrow existence from time, then return it. This is not philosophical speculation. It is experimentally verified. The Casimir effect, vacuum polarization, and spontaneous emission all prove that empty space is dynamically active. The theory begins with a simple but destabilizing anchor. If quantum fields can fluctuate in empty space, then space-time itself may be able to do the same. On the smallest scales, near the Planck length, quantum uncertainty may apply not just to particles, but to geometry. Space and time fluctuate. Causal structure becomes probabilistic. In this regime, before and after lose their classical meaning. The proposal is that our universe emerged as a quantum tunneling event. A tiny region of spacetime fluctuated into existence with positive energy stored in matter and radiation balanced by negative gravitational energy. The total energy remained exactly zero. No violation of conservation laws, no external cause. Once such a region appears, inflation can take over. Space expands exponentially. Quantum fluctuations are stretched to cosmic scales, seeding galaxies. What began as a microscopic instability becomes a universe billions of light years across. Now track the escalation across scale. Inflation freezes quantum noise into density variations. Those variations collapse under gravity into galaxies over hundreds of millions of years. Stars form, fuse elements irreversibly, and die. Heavy atoms disperse, planets condense, chemistry locks energy into molecular bonds, biology emerges, accelerating entropy production locally while increasing complexity. Every irreversible step depends on one thing, a universe that exists long enough for processes to complete. The tension is brutal. If universes can appear spontaneously, why don't they appear constantly? Why this universe? Why these constants? Some answers invoke selection effects. Only universes with stable physics persist long enough to be observed. Others appeal to deeper, unknown laws restricting what kinds of fluctuations are allowed. What destabilizes us here is not infinity, but contingency. Our universe may exist not because it was necessary, but because it was allowed, not planned, not triggered, just permitted by the structure of quantum reality. The Big Bang, in this view, is not a beginning of everything, but the moment when nothing stopped being quiet. Number 2, time emerged with the universe. This theory does not add a new substance before the Big Bang. It removes something instead, time. The conceptual anchor here is general relativity. In Einstein's framework, time is not a universal background taking away independently of the universe. It is a dimension woven together with space, shaped by matter and energy. Change the distribution of energy, and time itself changes its behavior. Run this idea backward far enough, and time begins to lose meaning. Near the Big Bang, densities approach the Planck scale. At that regime, quantum effects dominate spacetime. The smooth flow of time fractures into something undefined. Cause and effect blur. There is no global clock. In several approaches to quantum cosmology, the fundamental equations describing the universe do not include time at all. They describe relationships between configurations. Time emerges only when the universe becomes large, cool, and classical enough for irreversible processes to occur. In this view, asking what happened before the Big Bang is like asking what is north of the North Pole. The question assumes a coordinate system that does not exist beyond a boundary. Follow the escalation downward. On cosmic scales today, time is measured by expansion, by stellar lifetimes, by radioactive decay. In galaxies, stars evolve over millions to billions of years, irreversibly converting matter into energy. On planets, chemical reactions define biological clocks. On atomic scales, unstable particles decay with precise half-lives. All of these processes rely on an arrow of time driven by entropy increase. Near the Big Bang, entropy is paradoxically low, but rapidly increasing. That increase may be what brings time into existence. Before that increase, there is no flow to speak of, only a static quantum state. The tension is severe. If time emerged, what does emergence mean without time? How can something begin if beginning itself is a temporal concept? Physicists struggle here because language breaks before mathematics does. Some models suggest that what we perceive as time is a derived parameter, arising from correlations between quantum states. When those correlations become stable enough, time appears. When they are not, time dissolves. The destabilizing implication is profound. The universe may not have been created in time. Time may have been created in the universe. The Big Bang then becomes not the start of existence, but the start of temporal experience. Reality did not begin, duration did. And that leaves one final possibility, one that does not just challenge time, but challenges the stability of existence itself.
Number 1. Vacuum decay and the precarious nothingness. The most destabilizing possibility is not that something existed before the Big Bang, but that existence itself is only temporarily stable. At the foundation of modern physics lies the quantum vacuum. This is not empty space. It is the lowest energy configuration of all quantum fields. Every particle, every force, every constant of nature emerges from it. And crucially, the vacuum we inhabit may not be the true ground state of reality. It may be metastable. In quantum field theory, a system can appear stable while actually sitting in a local energy minimum, a false vacuum. Beneath it lies a lower energy state, separated by an energy barrier. Quantum mechanics allows tunneling through that barrier, not eventually, not predictably, but inevitably given enough time. If such a transition occurs, it does not happen gradually. A bubble of true vacuum nucleates spontaneously at a subatomic scale. Inside that bubble, the laws of physics are different. Particle masses change, forces rearrange, space-time itself redefines its structure. The bubble expands at nearly the speed of light. No signal outruns it, no warning propagates ahead of it. One moment, space exists. The next, it does not, in any meaningful sense. Now apply this backward. If our vacuum is metastable, then the Big Bang may not have been a creation event, but the aftermath of a prior vacuum decay. A previous vacuum state, governed by different constants and symmetries, transitioned into the one we now inhabit. The release of energy drove rapid expansion. Fields settled into new configurations. Particles gained mass. Time and space acquired their familiar behavior. Our universe is not fundamental. It is a phase. Trace the escalation across scale. The vacuum determines particle properties. Particle properties determine nuclear reactions. Nuclear reactions govern stellar life cycles. Stars seed galaxies. Galaxies host planets. Planets allow chemistry. Chemistry allows observers. Every irreversible process, fusion, decay, entropy increase, rests on the assumption that the vacuum remains stable long enough for complexity to unfold. The tension here is absolute. We can calculate vacuum stability using known particle masses, including the Higgs field. Current measurements suggest we may be uncomfortably close to instability, not doomed on human timescales, but not guaranteed eternity either. The unsettling edge is this: there may have been no before in any classical sense. There may have only been other vacuma,
other rule sets, other realities that decayed, giving rise to ours, and ours may someday do the same. The Big Bang becomes not a beginning in time, but a reconfiguration of existence. Reality did not start, it transitioned. And that makes the question what existed before dangerously incomplete, because what exists now may not be final.
Looking back toward the Big Bang is not about finding a clean beginning. It is about testing the limits of what existence, persistence, and time even mean. Across every theory, one message remains. The universe does not promise origins or permanence. What we call creation may simply be a boundary between descriptions, not the moment reality turned on. Humanity exists in a narrow interval. Stars still burn, galaxies still form, the vacuum remains stable. Time still flows in a direction we can follow. That combination may be exceptionally rare across all cosmic phases. What makes this era extraordinary is not that the universe began, but that, for now, it is structured enough to be understood. The deeper question is no longer where everything started. It is how long this moment can last.